All right, let's jump right in. Welcome to this explainer. Today, we're putting on the hat of a bioclimatic architect. That's someone who designs buildings heavily based on the local climate to ensure thermal comfort using mostly natural resources. We are going to explore the holistic life cycle approach to sustainable building efficiency. So, if you've ever wondered how the physical structures we live and work in can actually be engineered to work seamlessly with the laws of nature rather than fighting against them, you are absolutely in the right place. We're going to take a structural journey today, starting way out at macro-environmental concepts and zooming all the way down into internal mechanical systems.
40%. Seriously, just let that number sink in for a second. I want to kick things off by challenging a common perspective here. Buildings are responsible for an astounding 40% of all global energy use. Think about that. The spaces we inhabit consume nearly half of our energy resources, and whether directly or indirectly, this massive consumption produces some major carbon emissions. It really puts your monthly energy bill into perspective, doesn't it? So the big question is, how exactly do we fix this?
Well, there's a fascinating contrast between two fundamental energy concepts we need to unpack. We hear a lot about low-energy buildings, the ones equipped with fancy solar panels and ultra-efficient lighting. Now, that represents a low operational energy. But we really need to shatter the misconception that a building is truly green if its initial embodied energy, meaning the energy used to manufacture the materials, transport them, construct the building, and eventually demolish it, is massively wasteful. We literally see it all the time in modern cities, building these massive, sealed glass boxes in the middle of a desert and then relying on gigantic, energy-hungry AC units just to make them livable. Over a building's full life cycle, its carbon footprint can actually be way larger than a standard building if it was built using high embodied energy materials. True sustainability? It requires a careful balance of both.
So here is our syllabus for today. The true energy cost, masterful site planning, optimizing the building envelope, passive heating and cooling, and advanced efficiency systems.
Let's start with Section 1, the true energy cost, beyond operational gadgets.
The absolutely crucial point here is fully wrapping our heads around embodied energy. This is the total energy consumed across the entire lifespan of the building materials themselves. We're talking from the exact moment the raw materials are extracted, straight through manufacturing, transportation to the site, the heavy construction phase, and all the way to eventual demolition and disposal. Utilizing sustainable low-embodied energy materials is absolutely vital for long-term environmental benignity. If we get this wrong, literally all the energy-efficient gadgets in the world won't make up for the massive carbon debt incurred before move-in day.
Moving into Section 2, masterful site planning, the macro environment.
The natural environment is really our first line of defense. Strategic landscaping physically modifies the local temperature and actually dictates the airflow around a structure. By planting properly, we prevent the sun from directly striking and heating up building surfaces, and we stop hot re-radiation from the ground. Furthermore, vegetation actively lowers the adjoining air temperature through a biological process called evapotranspiration, which is actually very much like how sweating naturally cools our own skin. And here is a brilliant low-tech hack for composite climates. Planting deciduous trees. They provide dense cooling shade during the summer, but when they shed their leaves in the winter, they naturally allow the sun to penetrate and warm the building. Also, positioning water bodies near a building can naturally modify and stabilize those wild temperature fluctuations.
Orientation is another critical macro decision. In cold climatic regions, your primary goal is obviously to gain the maximum amount of solar heat. By simply rotating a building's orientation to align slightly east of south, you drastically alter its entire thermal profile. This specific angle maximizes solar heat gain because it ensures a much longer duration of exposure to the sun's path, effortlessly reducing heating requirements without flipping a single switch.
On to Section 3, optimizing the building envelope, the mesoenvironment.
To really grasp envelope efficiency, we need a precise technical signpost, and that's the surface-to-volume ratio. This is just the mathematical relationship between the volume of the space inside a building and the surface area enclosing it. The physics here is incredibly straightforward. For a given building volume, the more compact the shape, the lower the surface area exposed to the outside elements. And what does that mean? It means drastically less heat gain in the blistering summer and way less heat loss in the freezing winter. The form of the building also dictates the depth of the structure, which directly impacts how much artificial daytime lighting you'll eventually need. Now we can build these envelope optimizations directly into the structure itself. The roof and walls receive immense solar radiation. To combat this, we can use removable roof shading devices or even green, vegetated roofs to reduce overheating in summer while adding a great layer of insulation in winter. For walls, adjusting their thickness and incorporating internal air voids creates natural thermal breaks.
From a material science perspective, we want low thermal conductivity, appropriate thermal mass, and even the incorporation of phase change materials. These are really advanced materials that absorb and release thermal energy during the physical process of melting and freezing, maintaining a highly stable indoor temperature. It's a real game changer.
Next up is fenestration. This is basically just the architectural term for the strategic arrangement, sizing, and detailing of windows. Proper fenestration is heavily dictated by prevailing wind directions. By positioning windows on opposite walls, we easily create cross-ventilation. By positioning them at higher elevations, we utilize fluid dynamics, specifically the stack effect, where hot air naturally rises, just like smoke in a chimney, to naturally vent out that rising hot air. This dramatically increases the building's overall thermal efficiency.
All right, Section 4, Passive Heating and Cooling, Architectural Microfeatures.
A sunspace is such a brilliant example of a dual-purpose architectural microfeature. Ideally facing south, a sunspace acts as a completely passive solar heat trap. The transparent materials allow shortwave solar radiation to enter, which then turns into long-wave thermal radiation that cannot easily escape back out. It provides a wonderful, highly aesthetic living space or a place to grow plants, all while silently and continuously feeding pure warmth into the adjoining building structure.
You know, history often hands us some incredible solutions. Take traditional wind towers, or wind catchers, majestically integrated right into the architecture. They serve as entirely natural ventilation networks. Installed on top of buildings, they catch outside air and channel it deep down into the structure, establishing a continuous, natural airflow without the need for a single electrical fan. Now let's trace the specific physics of how we can actually supercharge these wind towers. By adding wetted columns, which are often made of unglazed ceramic conduit stacked lengthwise, or wetted cellulose pads, we introduce evaporative cooling. A small pump just keeps these surfaces wet. As the hot outside air passes through, the water evaporates, extracting sensible heat, that's the heat you can actually feel, right from the air. This cools the air, increasing its density. And because cold air is denser and heavier, it forces a really refreshing downward draft directly into the rooms below. It's a remarkably elegant application of basic thermodynamics.
There's also this brilliant subterranean solution, the earth-air tunnel heat exchanger. The science here relies on the simple fact that a few meters below ground, the Earth's temperature remains almost entirely constant year-round. By routing an underground pipe or tunnel from a wind tower to the building, ambient air is naturally forced underground. In the summer, the cooler subterranean earth extracts heat from the air, providing sensible cooling. In the winter, the earth is actually warmer than the freezing outside air, naturally pre-warming it before it even enters the building.
Finally, Section 5, Advanced Efficiency Systems, Internal Mechanics.
Okay, so even with the absolute best passive design in the world, some mechanical assistance is often needed. We can use roof ventilators that look and function very much like vertical axis windmills. As the wind naturally turns their light blades, an air sweeper at the base continuously sweeps out large volumes of hot, stale interior air. Combine this with increased passive lighting designs, and you absolutely drastically reduce your daytime electrical loads for both lighting and mechanical ventilation. And when active air conditioning is strictly necessary, the modern system of choice is the Variable Refrigerant Volume or VRV system. Unlike a conventional HVAC that wastes a ton of energy on a fixed load, a VRV is highly efficient under partial load conditions. It circulates variable amounts of refrigerant directly to exactly where it's needed, allowing for completely customized individual zoning. Best of all, it entirely eliminates the need for massive plant rooms and really heavy chilled water piping and ducting. Overall, a VRV system contributes to roughly 15% energy savings compared to standard central air conditioning baselines.
So we've traveled from the macro environment of site planning all the way down to the micro mechanics of evaporative cooling and advanced VRV systems. But I want to leave you with this final provocative thought today. If a building's true environmental cost is determined long before the foundation is even poured, locked into the embodied energy of its very materials, how must we redesign our modern cities moving forward? Should we continue prioritizing flashy operational gadgets, or is it time we fundamentally return to the holistic life cycle architecture of efficiency? Definitely something to think about. Thank you so much for joining me in this explainer, and keep questioning the structures around you.